Okay, so what we're going to learn today is the divisibility proofs using proof by mathematical induction. So our example today is we're looking at the expression 9n plus 3, and we assert that this is going to be divisible by 4 whenever we're looking at a positive integer value of n. So because we're doing proof by induction, what is the first thing we're always going to try and prove, please, Brad?
Base case.
Base case. You're always going to go for the base case. Now, for the base case, what are we going to sub in for n? We're looking at all positive integers. Brad?
1.
1. Why 1 and not 0?
It's the first term.
Yeah, it's neither, it's not positive. 0 is neither negative nor positive. And secondly, if you assert it's an integer, you're probably going to cause a fight amongst mathematicians. Some say yay, others say nay. So we're looking at p of 0, or you could write it as p0, like that. So what we're effectively going to do is we're going to say a base case, oh, sorry, not 0. Exactly what I said I wasn't going to do. P1. What we're going to do is we're going to substitute 1 in for n. So the expression becomes 9 to the power of 1 plus 3, which expanded out to 9 plus 3, which is 12. And if you don't believe 12 is divisible by 4, then you just factorize it. So you could leave it as 12 because everyone knows 12 is divisible. But if you really want to show the reader that it's divisible, you can factorize out 4, and therefore P1 is true. Now, since we know the base case is true, we move on to the inductive step, or the inductive case. Okay, confident face, if you remember, what do we assume for the inductive case here? Nick, notice you're not looking necessarily confident, but you're looking relaxed.
Thanks. So basically, the inductive case is true. Assume.
What do we say? Assuming what?
Assuming that.
This is P of n.
Oh, it's P?
P of, or pk is true.
Yep.
Then what we find is that our P of n is going to be, oh sorry, P of k is going to be 9k plus 3. And if 9k plus 3 is divisible by 4, what would it equal to? Remembering that 9 to the power 1 plus 3 was equal to 4 times this number here. It's going to be able to be 4 lots of something. We don't know what. So we can say A, and then we can assert that A is just an integer. So the fancy Z there means it's an integer. So A is a type of integer. And because I've defined A, I should also define K as a positive integer. Are we good so far?
Maybe.
So we're going through the method to show mathematically whether something's divisible by not, using proof or using mathematical induction. Induction always states that we check to see that the first case is true, in which case it is. And if that's true, then we make an assumption and then prove the k plus 1th term. So assuming that's true, hence we're going to have P of k plus 1. And here's where it gets a little bit fun or upsetting, depending on if you know what you're doing or not. For pk, or P of k plus 1, it's going to be 9k plus 1 plus 3. And I would like to say that it's equal to an integer multiple of 4. But we can do better than that. What we want to do is we want to make this with a factor of 4. We can't just assume. So what we're going to do is a bit of fancy rearranging. First thing is index laws. 9 to the power of k plus 1. If I don't want a plus 1 there, what I can do is I can take out a factor of 9. And it becomes 9 times 9 to the power of k. Do we remember that? Or I can go 9 to the power of 1 times 9 to the power of k. You add the exponents together, so it's k plus 1. Are we cool with that? We don't need that there, so I'll do it a different color. Okay, then here's where it's going to get a bit funky. Using P of k. So using what we've already defined here, we know that 9k plus 3 equals 4a. We want to do a substitution, but it's not so simple, is it? We have 9k plus 3, and over here we've got a 9 times 9k plus 3. We can't really get around that yet. So what we can do is we can just substitute it in such a way that it goes, let's say, 9, and then I'll put it here for now, 9k, and I'll save some space. 9k plus 3. Next step, I'm going to put in some brackets. Do we have an expression for 9k?
Yeah.
Mr. Leishman?
4a takes 3.
Okay, so 9k plus 3 is 4a. Therefore, we're going to find that 9k is 4a, take 3. Do you see what's happened there?
Yeah.
So we've used that P of k and we've cleverly rearranged it. Putting this in, that becomes 4a take 3. And by expanding this out, we're going to get 36 a's take 27 plus 3. Collecting like terms, that's going to be 24. And then factorizing for a factor of 4, we get 9a take 6. We cool with that? So the take,
9 times 4a take 3.
whereabouts? Here?
Yeah.
Okay. Do you see that 9 to the power of k plus 3 equals 4a? What we want to do is we want to get this P of k into our expression over here. So what we do is we try and make it so there's a 9k. And then when we've got a 9k, we get this guy over here. And we rearrange this expression so that we can get 9k as substitute as 4a take the 3. So we move the 3 to the right hand side. Does that make sense?
Yeah.
So the real, again, I don't want to use the word trick. The strategy for dealing with these is you modify your P of k expression.
So how come with the brackets the to the power of k disappeared?
With the brackets.
Where it goes 9 times.
Substitution.
12.
In place of 9k, we can replace it with the expression 4a take 3. Does that make sense?
Yeah.
So they're like for like. This is equivalent to that. And if that is equivalent to that, then rather than writing 9k, we can put that in. And that allows us to pull out a factor of 4. Is that cool?
Yeah.
And then to finish it off, since P of 1 is true, and P of k plus 1 is true. When ever P of k is true, whoops. Oh, that's not good at all. Then we can assume that, or we've proven that P of n is true for all. So the upside down A means for all values of n that are positive integers. Seem cool?
Yes, sir.
Any questions?